We studied first order ordinary differential equation. This week we will start to study second order ordinary differential equations, and we will study reduction of order. So this week we will start this with these subjects, and next week we will continue to solve homogeneous differential equations, second order homogeneous differential equations, and we will learn the method of undetermined coefficients method. Last time we studied separable differential equations, homogeneous, exact, linear, and Bernoulli differential equations. So in every exam, I am planning to ask separable differential equations in all of your exams because they are very easy to solve. I think I don't want you to get low grades, so I'm planning to ask separable in the finals also, in your exams also. So let's start second order ordinary differential equations. A second order ordinary differential equation is a linear equation in the standard form. If it can be written as like this, we say second order, so we should have a second derivative, right? So y double prime plus pxy prime first derivative plus qxy is equal to r of x. So we say in standard form if the coefficient of y double prime is equal to 1, and if it is called non-linear, if it cannot be written in this form. So okay, I make a note. If the coefficient of y double prime is not 1, then it is a non-standard form, but we can divide the equation to get into the standard form. Okay, let me give examples for this. So for example, okay, let's say y double prime plus 16 y prime plus sine of x y is equal to ln x, let's say. So this is linear in standard form, or maybe I should write second order linear in standard form. So let's say we have e to the power y double prime x plus 8y prime plus 3x y is equal to sine x. So this is second order linear, but not in standard form. But we can divide, divide by, so this e to the power x to get the standard form. Okay, we can divide because e to the power x is never 0. E to the power x y prime plus 3x e to the power x y is equal to sine x over e to the power x. So this is, or we can write like this, 8 e to the power minus x y prime plus 3x e to the power minus x y is equal to sine x e to the power minus x. So this is in, now it is in standard form. Great, and we have another definition, homogeneous and non-homogeneous equation, and it is different from the first order differential equations. So recall that we studied first order homogeneous equations, but in second order we have a different. So the equation y double prime p of x y prime plus q of x y is equal to r of x. In the equation, in this equation, so this is, sorry, I will y double prime. So in this equation, if r of x is equal to 0, then the equation is called, homogeneous differential equation. If r of x is not equal to 0, then it is called non-homogeneous. It is called non-homogeneous. So, for example, y double prime plus 16y prime is equal to 0 is homogeneous. But so if we have r prime, so r of x, 16y prime, let's say it is equal to e to the power x. So this is non-homogeneous. So this is non-homogeneous. You see, it is equal to 0. It is equal to e to the power x. So we check this r of x if it is equal to 0, then it is a homogeneous differential equation, and this is non-homogeneous differential equation. Okay, let me give a non-linear, maybe non-linear, non-homogeneous differential equation. So let's say you have y double prime plus x squared y prime plus x cubed y is equal to let's say 0. So because of this, the coefficient y, so this is a nonlinear. So this is second order, and it is homogeneous because of this. It is equal to 0, homogeneous, but it is nonlinear. So we want y double prime plus p of x y prime plus q of x y is equal to r of x. So this is linear. You see, the coefficients only depends on x. So I want to emphasize this. So because of this y term, so this is not, it is not a function of x only. So we have y there. So it is nonlinear. Great. So for homogeneous differential equations, okay, for homogeneous differential equations, so they are of the form, we say homogeneous, so r of x is 0 here. So for homogeneous equations, if we have two solutions, y1 and y2 are two solutions of the homogeneous differential equations, then any linear combination, of y1 and y2. What do we mean by a linear combination? What is any linear combination of y1 and y2? So which is so we take any linear combination c1 y1 plus c2 y2 for any constants. So we combine them. So for any constants c1 and c2. So whenever we have this case, we have two solutions, y1 and y2, then any linear combination is also a solution. So any linear combination is also a solution of homogeneous differential equation. Okay, let me give you an example so it will be clear. So check that, for example, so check that y1 is equal to cosine x and y2 is equal to sine x are solutions of y double prime plus y is equal to 0 and their linear combination okay, their linear combination, let's say c1 cosine x plus c2 sine x is also a solution. So we have this, let's solve it. We have this differential equation, y prime plus y is equal to 0. Okay, we want to check y1 cosine x is a solution. We need to take the first derivative. It is minus sine x. Y double prime minus cosine x. So what does, so let's put it in the equation. So we have minus cosine x plus cosine x is equal to 0. So it satisfies the equation, so it is a solution. Okay, let's check the second one. y2 is equal to sine x. What is the first derivative? It is cosine x. What is the second derivative? It is minus sine x. And we see that second derivative of y2 plus y2 is equal to minus sine x plus sine x, so which is equal to 0. So it is also a solution. So what about y is equal to c1 cosine x plus c2 sine x? We need to take the first derivative. So it is minus c1 sine x plus c2 cosine x. What about the second derivative? It is minus c1 cosine x plus minus c2 sine x. As you can see, y double prime plus y is equal to 0. So if we put it in the equation, we get 0. C1 cosine x, c2 sine x, the linear combination. So linear combination is also a solution, because we need this to get to, so later we will say, okay, we find the solutions, and when we get the linear combination, we will get the general solution for the homogeneous differential equation. So this is, we need this to solve. But we need to be careful to get the general solution. We need to be more careful, because so we see that y1 is equal to cosine x is a solution, and let's say we have another y3. So let's say 5 cosine x is also a solution. But we can see that y3 is equal to 5 y1, right? So they are related. So y3 depends on y1. So y3, this 5 cosine x depends on y1. But if you compare to sine x, so cosine x doesn't depend on y2, right? So cosine x doesn't depend on y2. So we cannot get, so we cannot write y2 as a multiple of y1. So, but y2 sine x so cannot be written as let's say c times y1, right? Some multiple, like we cannot write this. Sin x is not equal to some multiple of cosine x. So they say, so that's why we say y2 doesn't depend on y1. So this is, we have some definition here, linear dependence. So what do we mean by actually is this, y2 is linearly independent. So they are, y2 and y1 are linearly independent. So we cannot write one of them as a multiple of the other. So we say, okay, two functions, y1 and y2 are linearly independent if c1 y1 plus c2 y2 is equal to 0, then this is only possible when c1 is equal to 0 and c2 is equal to 0. Okay, I will. Okay, and so there is an easy way to understand the linear dependence. We look at some determinant, or let me make a note, short note here. So otherwise, so if c1 is equal to not equal to 0, or c2 is not equal to 0, then we can write like c1 y1 is equal to minus c2 y2, and we can write y1 as a multiple of you see, multiple of y2, like, okay, so this is linearly dependent. So in this case they are linearly dependent, like in this case. So okay, y3 is 5 cosine x, so they are linearly dependent, but y1 and y2, they are linearly independent. Okay, as I said, in general, so okay, maybe okay, I will do it for second order. Let y1 and y2 be real functions which are differentiable. Then the determinant. Okay, we will learn matrices after this, but we have to give. So we will take this determinant y1, y2, y1 prime, y2 prime. So this is a 2 by 2 matrix. So we will learn this in detail after the second order differential equations. So we will study matrices. But we know how to take the derivative of, determinant of this one. So we multiply this, and we subtract the multiplication of the other diagonal. So it is y1, y2 prime minus y2, y1 prime. So this is called the, this determinant is called the Wronskian of the functions. Y1 and Y2. Y1 and Y2, because we have something nice. If this Wronskian is not equal to 0, then we say that two functions are linearly independent. So we have a nice theorem. So we will not prove it here, but so we have this. So the solutions of Y1 and Y2 of a second order homogeneous differential equation are linearly independent if and only if, so we have something nice, if and only if this Wronskian, this determinant y1, y2 is not equal to 0. Great. Okay, let me summarize. So whenever you have y double prime plus p of x y prime plus q of x y is equal to 0, and y1 and y2 are two solutions of it, then y1 and y2 are linearly independent if and only if, so we have, okay, maybe I will write it like this, sorry, independent if and only if the Wronskian y1, y2, oops, sorry, so which is equal to this determinant y1, y2, y1 prime, y2 prime is equal to y1, y2 prime minus y2, y1 prime is not equal to 0. Okay, let me give an example. So we solve this y1 cosine x and y2 is equal to sine x are, so my claim is, so they are linearly independent solutions of y double prime plus y is equal to 0. Why? Since, okay, let's look at this Wronskian y1, y2, so which is cosine x, sine x. So we will look at this determinant. So we write y1 and y2 in the first row, and in the second row we write its derivative. What is the derivative of cosine x? It is minus sine x. What is the derivative of sine x? It is cosine x. Okay, we take this determinant. As I said, we will multiply this and we will write plus. So it is cosine square x, and we multiply this and we take its minus. So it is minus sine square x, so which is cosine square x plus sine square x, so which is equal to 1 and which is not equal to 0, right? So if you want, you can check with cosine x. Y2 is equal to 5 cosine x. So you can check this. So the Wronskian, okay, let's write y1, y3. So this should be 0. So they are linearly dependent. Sorry, check. Check this. They are linearly dependent. Because we can't see the dependence, right? It is 5 times y1, so it depends on y1. Okay, let's do one more example. Okay, show that y1x e to the power 2x and y2x e to the power minus 2x are linearly independent solutions of y double prime minus 4y is equal to 0. Okay, but it says the solution, so we need to check also they are the solutions. Okay, we have y1 is equal to e to the power 2x. Let's take the first derivative. It is 2e to the power 2x. Let's take the second derivative. It is 4e to the power 2x. And we can see that y1 prime, double prime minus 4y1 is equal to 4e to the power 2x minus 4e to the power 2x. So it is a solution. What about the second one, e to the power minus 2x? Take the first derivative, minus e to the power minus 2x. Take the second derivative, it is 4 times e to the power minus 2x. Similarly, so y double prime is equal to 4 e to the power minus 2x. Okay, sorry, I should write y double prime minus 4 y2 double prime. So it is 4e to the power minus 2x minus 4e to the power minus 2x. So this is it is a solution. What about are they linearly independent or dependent? We will check this Wronskian. So y1, y2, y1 prime, y2 prime. First derivative, okay, e to the power 2x, e to the power minus 2x. Let's take this first derivative and write it in the second row. Minus e to the power minus 2x. Okay, we multiply this diagonal and write plus. We multiply this diagonal and write minus. And we will get minus 2e to the power 2x times e to the power minus 2x minus 2 times e to the power 2x times e to the power minus 2x. So we know that e to the power, 2x times e to the power minus 2x. So this is equal to 2x minus 2x e to the power 0. So this is 1. So we have minus 2, it is minus 4. So since this Wronskian y1, y2 is not equal to 0, there y1 and y2 are linearly independent. Great, I think it is clear. So why we studied this? Because we will get the general solution of the homogeneous differential equations. Okay, let's write. Okay, general solution. What do we mean? If y1 and y2 are linearly independent solutions of second order homogeneous linear, so we don't know what will happen if we have a non-linear differential equation, but if we have a second order homogeneous linear differential equation, so which can be given as let's say ax y double prime plus p of x y prime plus q of x, sorry, y is equal to r of x. So we don't need to have s in standard form. So this is always true. If it is equal to r of x, oh no, we said homogeneous. So r of x is equal to 0, right? We said homogeneous. Okay, that is great. R of x is equal to 0. Then y is equal to c1 y1 plus c2 y2 is the general solution. So is a general solution of the given of the homogeneous differential equation where C1 and C2 are arbitrary constants. So this is important. So in this example, then what is the general solution in this last example? So in this example, we see that y1 e to the power 2x and y2 e to the power minus 2x are linearly independent solutions of y double prime minus 4y is equal to 0. So we see that they are linearly independent. Then y is equal to c1 e to the power 2x plus c2 e to the power minus 2x is the general solution. So we have the general solution. Okay, and we have another concept, so initial value problem. Initial value problem. So we write initial value problem. If you remember, in the first order differential equations, we also have the initial value problem. We have the initial conditions, but in this case, we will have two initial conditions, y double prime plus q of x y is equal to 0. So we have two conditions, y x0 is equal to, let's say, y0, y prime x0 is equal to, let's say, y1, or let's say, okay, maybe you will confuse, let's say maybe a and b. So this is the initial value problem. We have second order. We have two conditions. We have two conditions given at the same value at x0, right? So we have two conditions given at the same value. Let's say x0 in this case. Okay, let's do an example and end this lecture. Example, solve the initial value problem. Y double prime minus 4y is equal to 0, y0 is equal to 1, and y prime 0 is equal to minus 4. So this is our initial value problem. We know the general solution. Y is equal to c1. Okay, I write it there. E to the power 2x plus c2 or e to the power minus 2x is the general solution. So we know this is the general solution. But we are asked to find the solution of this initial value problem. So the solution that satisfies these two conditions. But we can find C1 and C2 using these conditions. Y0 is equal to 1, y prime 0 is equal to minus 4. Okay, let's take y prime. So it is 2c1 e to the power x plus, minus 2c2 e to the power minus 2x. Okay, y0 is equal to 1. So when x is equal to 0, we will put y is equal to 1 into y in this one. So y is equal to c1 e to the power 0 plus c2 e to the power 0. And in this case, it is equal to 1. So we know c1 plus c2 is equal to, 1. Because e to the power 0 is equal to 1. And what about y prime 0 is equal to minus 4? So this means that when we put x is equal to 0, y must be minus 4. And we will put in this time in this equation. So y prime is equal to 2c1 e to the power 0 minus 2c2 e to the power 0 is equal to minus 4. So we have 2c1 minus 2c2 is equal to minus 4. So we will solve using this c1 plus c2 is equal to 1 and 2c1 minus 2c2 is equal to minus 4. So we can find c1 and c2, right? So multiply the first one with 2. So 2c1 plus 2c2 is equal to 2. Okay, we add this. So we have 4c1 is equal to minus 2. c1 is equal to minus 2 over 4, minus 1 over 2. And we know c1 plus c2 is equal to 1. So c2 is 1 minus c1. So c2 is 3 over 2. So what is the then solution of the initial value problem is, so y is equal to c1 y1 plus c2 y2. We find c1 minus 1 over 2 e to the power 2x plus 3 over 2 e to the power minus 2x. So this is our solution for the initial value problem.